Let's start by imagining we measured the mass of a bunch of mice. The red dots represent mice that are not obese, and the green dots represent mice that are obese. Based on these observations, we can pick a threshold, and when we get a new observation that has less mass than the threshold, we can classify it as not obese. And when we get a new observation with more mass than the threshold, we can classify it as obese. However, what if we get a new observation here? Because this observation has more mass than the threshold, we classify it as obese. But that doesn't make sense because it is much closer to the observations that are not obese. So this threshold is pretty lame. Can we do better? Yes. Going back to the original training dataset, we can focus on the observations on the edges of each cluster and use the midpoint between them as the threshold. Now, when a new observation falls on the left side of the threshold, it will be closer to the observations that are not obese than it is to the obese observations. So it makes sense to classify this new observation as not obese. Bam! Oh no, it's a terminology alert. The shortest distance between the observations and the threshold is called the margin. Since we put the threshold halfway between these two observations, the distances between the observations and the threshold are the same and both reflect the margin. When the threshold is halfway between the two observations, the margin is as large as it can be. For example, if we move the threshold to the left a little bit, then the distance between the threshold and the observation that is not obese would be smaller, and thus the margin would be smaller than it was before. And if we move the threshold to the right a little bit, then the distance between the obese observation and the threshold would get smaller. And again, the margin would be smaller. When we use the threshold that gives us the largest margin to make classifications, heads up, terminology alert, we are using a maximal margin classifier. Bam? No bam. Maximal margin classifiers seem pretty cool, but what if our training data looked like this? And we had an outlier observation that was classified as not obese, but was much closer to the obese observations. In this case, the maximum margin classifier would be super close to the obese observations, and really far from the majority of the observations that are not obese. Now, if we got this new observation, we would classify it as not obese, even though most of the not obese observations are much further away than the obese observations. So maximal margin classifiers are super sensitive to outliers in the training data, and that makes them pretty lame. Can we do better? Yes! To make a threshold that is not so sensitive to outliers, we must allow misclassifications. For example, if we put the threshold halfway between these two observations, then we will misclassify this observation. However, now when we get a new observation here, we will classify it as obese. And that makes sense because it is closer to most of the obese observations. Choosing a threshold that allows misclassifications is an example of the bias-variance trade-off that plagues all of machine learning. In other words, before we allowed misclassifications, we picked a threshold that was very sensitive to the training data. It had low bias. And it performed poorly when we got new data. It had high variance. In contrast, When we picked a threshold that was less sensitive to the training data and allowed misclassifications, so it had higher bias, it performed better when we got new data, so it had low variance. Small BAM. Oh no, it's another terminology alert. When we allow misclassifications, the distance between the observations and the threshold is called a soft margin. So the question is, how do we know that this soft margin is better than this soft margin? The answer is simple. We use cross-validation to determine how many misclassifications and observations to allow inside of the soft margin to get the best classification. For example, if cross-validation determined that this was the best soft margin, then we would allow one misclassification and two observations that are correctly classified to be within the soft margin. BAM! When we use a soft margin to determine the location of a threshold, brace yourself, we have another terminology alert. Then we are using a soft margin classifier, aka a support vector classifier, to classify observations. The name support vector classifier comes from the fact that the observations on the edge and within the soft margin are called support vectors. Super small BAM. Note, if each observation had a mass measurement and a height measurement, then the data would be two-dimensional. When the data are two-dimensional, a support vector classifier is a line. And, in this case, the soft margin is measured from these 2 points. The blue parallel lines give us a sense of where all of the other points are in relation to the soft margin. These observations are outside of the soft margin, and this observation is inside the soft margin and misclassified. Just like before, we used cross-validation to determine that allowing this misclassification results in better classification in the long run. BAM! Now, if each observation has a mass, a height, and an age, then the data would be three-dimensional. Note, the axis that age is on is supposed to represent depth, and these circles are larger in order to appear closer and thus younger. And these circles are smaller in order to look further away and thus older. When the data are three-dimensional, the support vector classifier forms a plane instead of a line. And we classify new observations by determining which side of the plane they are on. For example, if this were a new observation, we would classify it as not obese since it is above the support vector classifier. Note, if we measured mass, height, age, and blood pressure, then the data would be in 4 dimensions. And I don't know how to draw a 4-dimensional graph. Wah wah. But we know that when the data are one-dimensional, the support vector classifier is a single point on a one-dimensional number line. Psst! In mathematical jargon, a point is a flat affine zero-dimensional subspace. And when the data are in 2 dimensions, the support vector classifier is a one-dimensional line in a 2-dimensional space. Psst! In mathematical jargon, a line is a flat affine one-dimensional subspace. And when the data are 3-dimensional, the support vector classifier is a 2-dimensional plane in a 3-dimensional space. Psst! In mathematical jargon, a plane is a flat affine 2-dimensional subspace. And when the data are in 4 or more dimensions, the support vector classifier is a hyperplane. Psst! In mathematical jargon, a hyperplane is a flat affine subspace. Note: technically speaking, all flat affine subspaces are called hyperplanes. So, technically speaking, this one-dimensional line is a hyperplane. But we generally only use the term when we can't draw it on paper. Small bam, because this is just more terminology. Ugh. Support vector classifiers seem pretty cool because they can handle outliers, and because they can allow misclassifications, they can handle overlapping classifications. But what if this was our training data and we had tons of overlap? In this new example, with tons of overlap, we are now looking at drug dosages. And the red dots represent patients that were not cured. And the green dots represent patients that were cured. In other words, the drug doesn't work if the dosage is too small or too large. It only works when the dosage is just right. Now, no matter where we put the classifier, we will make a lot of misclassifications. So, support vector classifiers are only semi-cool since they don't perform well with this type of data. Can we do better than maximal margin classifiers and support vector classifiers? Yes. Since maximal margin classifiers and support vector classifiers can't handle this data, it's high time we talked about support vector machines. So let's start by getting an intuitive sense of the main ideas behind support vector machines. We start by adding a y-axis so we can draw a graph. The x-axis coordinates in this graph will be the dosages that we have already observed. And the y-axis coordinates will be the square of the dosages. So, for this observation, with dosage equals 0.5 on the x-axis, the y-axis value equals dosage squared, which equals 0.5 squared, which equals 0.25. Now we use dosage squared for this y-axis coordinate, and then we use dosage squared for the y-axis coordinates for the remaining observations. Since each observation has x and y-axis coordinates, the data are now two-dimensional. And now that the data are two-dimensional, we can draw a support vector classifier that separates the people who were cured from the people who were not cured. And the support vector classifier can be used to classify new observations. For example, if a new observation had this dosage, then we could calculate the y-axis coordinate by squaring the dosage and classify the observation as not cured because it ended up on this side of the support vector classifier. On the other hand, if we got a new observation with this dosage, then we would square the dosage and get a y-axis coordinate and classify this observation as cured because it falls on the other side of the support vector classifier. Bam! The main ideas behind support vector machines are 1. Start with data in a relatively low dimension. Psst. In this example, the data started in one dimension. 2. Move the data into a higher dimension. Psst. In this example, we move the data from one dimension to two dimensions. 3. Find a support vector classifier that separates the higher dimensional data into two groups. That's all there is to it. Double bam! Going back to the original one-dimensional data, you may be wondering why we decided to create y-axis coordinates with dosage squared. Why not dosage cubed? Or pi divided by 4 times the square root of dosage? In other words, how do we decide how to transform the data? In order to make the mathematics possible, support vector machines use something called kernel functions to systematically find support vector classifiers in higher dimensions. So let me show you how a kernel function systematically finds support vector classifiers in higher dimensions. For this example, I use the polynomial kernel, which has a parameter, d, which stands for the degree of the polynomial. When d equals 1, the polynomial kernel computes the relationships between each pair of observations in one dimension. And these relationships are used to find a support vector classifier. When d equals 2, we get a second dimension based on dosages squared. And the polynomial kernel computes the two-dimensional relationships between each pair of observations. And those relationships are used to find a support vector classifier. And when we set d equal 3, then we would get a third dimension based on dosages cubed. And the polynomial kernel computes the three-dimensional relationships between each pair of observations. And those relationships are used to find a support vector classifier. And when d equals 4 or more, then we get even more dimensions to find a support vector classifier. In summary, the polynomial kernel systematically increases dimensions by setting d, the degree of the polynomial. And the relationships between each pair of observations are used to find a support vector classifier. Last but not least, we can find a good value for d with cross-validation. Double bam! Another very commonly used kernel is the radial kernel, also known as the radial basis function kernel. Unfortunately, the radial kernel finds support vector classifiers in infinite dimensions, so I can't give you an example of what it does exactly. However, when using it on a new observation like this, the radial kernel behaves like a weighted nearest neighbor model. In other words, the closest observations, aka the nearest neighbors, have a lot of influence on how we classify the new observation. And observations that are further away have relatively little influence on the classification. So, since these observations are the closest to the new observation, the radial kernel uses their classification for the new observation. Bam! Now, for the sake of completeness, let me mention one last detail about kernels. Although the examples I have given show the data being transformed from a relatively low dimension to a relatively high dimension, kernel functions only calculate the relationships between every pair of points as if they are in the higher dimensions. They don't actually do the transformation. This trick, calculating the high-dimensional relationships without actually transforming the data to the higher dimension, is called the kernel trick. The kernel trick reduces the amount of computation required for support vector machines by avoiding the math that transforms the data from low to high dimensions. And it makes calculating the relationships in the infinite dimensions used by the radial kernel possible. However, regardless of how the relationships are calculated, the concepts are the same. When we have two categories, but no obvious linear classifier that separates them in a nice way, support vector machines work by moving the data into a relatively high-dimensional space and finding a relatively high-dimensional support vector classifier that can effectively classify the observations.
참조 동영상에서 다룬 서포트 벡터 머신에 대해서 강의하도록 하겠습니다. 서포트 벡터의 목적은 이러한 데이터들이 있을 때 이들을 구별할 수 있는 리니어 하이퍼플레인 혹은 디시전 바운더리를 찾는 것입니다. 빨간 사선이 하나의 가능한 솔루션이 될 수 있습니다. 점선으로 표시된 또 다른 사선도 솔루션이 될 수 있습니다. 가능한 솔루션은 아주 많을 수 있기 때문에 우리는 이 중에 어떤 것이 좋은 솔루션인지를 찾는 방법이 필요합니다. 바운더리 B1과 B2 중에 어떤 것이 더 나은 것인지, 그리고 더 낫다는 것을 어떻게 define, 정의하는지에 대해서 알아보도록 하겠습니다. 척도는 margin입니다. Find hyperplane maximizes the margin. 마진을 최대화하는 하이퍼플레인을 찾는 것이 목적입니다. B1의 마진이 B2의 마진보다 큰 것을 알 수 있습니다. 하이퍼플레인의 식은 W 벡터에 X 벡터를 곱하고 B를 더한 것으로 나타낼 수 있습니다. 여기서 W와 B는 모델의 매개 변수이고 X는 애트리뷰트입니다. B1은 하이퍼플레인 혹은 초평면으로 wx 더하기 b equal 0로 표현할 수 있습니다. 이의 평행한 초평면 bi1과 bi2도 wx 더하기 b equal -1과 플러스 1로 표현할 수 있습니다. 의사결정 경계의 마진은 이 두 초평면의 거리에 의해서 결정되는데 오른쪽 아래에 마진의 값이 2 나누기 W 벡터의 크기로 정의되어 있습니다. 리니어 SVM 모델은 다음과 같이 정의될 수 있습니다. fx 값은 만일에 wx 더하기 b가 1보다 같거나 크면 1로 정의되고 -1보다 같거나 작으면 -1로 정의됩니다. 모델을 학습하는 것은 w 벡터와 b의 값을 결정하는 것과 같습니다. 다음은 트레이닝 데이터로부터 W 벡터와 B 값을 찾는 방법을 알아보도록 하겠습니다. 리니어 SVM의 학습입니다. Objective, 목적은 다음의 마진을 maximize 하는 것입니다. 이는 L equal W 자승 나누기 2의 식을 minimize 하는 것과 동등한 것입니다. 이때 W는 yi가 1과 -1이 되는 조건의 constraint들을 만족해야 됩니다. 이것은 constrained optimization 문제인데 프로그램을 짜실 때는 머신러닝에서 제공하는 API를 활용하시면 됩니다. decision boundary는 support 벡터에만 의존합니다. 만약 데이터셋이 바뀌어도 support 벡터가 같다면 decision boundary는 변하지 않습니다. SVM으로 분류를 하는 방법은 W와 B 값을 찾은 뒤에는 test record xi를 하이퍼플레인, 초평면의 식에 대입하면 됩니다. 아래 식을 보면 wx 더하기 b가 1보다 같거나 크면 클래스 1로 분류를 하고 -1보다 같거나 작으면 클래스 -1로 분류를 합니다. 다음 사례는 마진 안에 데이터들이 있어서 선형적으로 구별하기 어려운 경우입니다. 이 경우에는 zeta 함수로 표시된 slack variable 개념을 도입합니다. 미니마이즈 하고자 하는 함수에 zeta가 반영된 것을 볼 수 있습니다. 또한 초평면식에도 zeta가 도입되었습니다. slack 변수를 조절하면 초평면을 얻을 때 에러는 두 개 있지만 마진이 큰 B1을 얻을 수도 있고 에러도 없고 마진도 적은 B2를 얻을 수도 있습니다. 이 분류기의 목적에 따라서 에러와 마진을 옵티마이즈하는 하이퍼플레인을 찾도록 합니다. 다음은 우리가 얻고자 하는 decision boundary가 리니어하지 않은 경우입니다. 아래 그림에 보면 attribute x1과 x2에 대해서 원 모양의 바운더리가 필요한 것을 알 수 있습니다. 이 경우에 데이터 트랜스포메이션을 통해서 리니어 바운더리를 얻도록 합니다. 리니어한 decision 바운더리를 얻기 위해서 x1을 x1 자승 -x1으로 트랜스폼했고 x2를 x2 자승 -x2로 트랜스폼했습니다. decision boundary 식을 보면 attribute expect를 phi의 식을 사용해서 high dimensional space로 매핑한 것을 볼 수 있습니다. 이러한 방법은 non-linear boundary를 만드는데 유용하지만 모든 데이터 타입에 적용할 수 있는 것은 아닙니다.